terms in each equation. The direction vector, which is going from 1, 0 to 0, 1, what would that vector be? Keep in mind, again, paying very careful attention to prepositions. Based on the fact that this is worded as going from 1, 0 to 0, 1, suggests to me that the tail of this vector would be 1, 0, and the head of the vector would be 0, 1. So if you do head minus tail, yeah, head minus tail would be -1 for I and +1 for j. Those become your t coefficients. -1t and then +1t. So the parameterization of this curve that goes from the point 1, 0 to the point 0, 1, that's it. But keep in mind, you also need the t values. What are the t values that give me those 2 points, beginning with this one and ending with that one? What do you almost always begin t with? 0. And then, if every single time your direction vector takes you from the beginning point to the end point, in other words, if you're connecting 2 points on a line segment, the beginning point is the tail of the vector that you got here, the ending point is the head, then what's the maximum value of t that you're going to use? 1, because you're adding 1 copy of these ij components to those xy coordinates to end up at that xy coordinate. So it'll always be from 0 to 1 if you use the starting point that you begin with, 1, 0 for x and y, and then you use the direction vector that goes from beginning point to end point. Okay? So just to double check and make sure. If I want to parameterize the line segment in the xy plane that goes from the point -6, 3 and ends up at the point 8, -5. Remember, your starting point is always your constant terms. Your direction vector is going to be head minus tail. So your head minus tail x is going to give you a 14i. Head minus tail y is going to give you a -8j. So if you go from beginning to end, tail to head on your line segment that you're trying to parameterize, you need to add 1 copy of these components to these coordinates to end up at the second point. So there's my constant terms. These are my t coefficients. And this will always be your range of t. Because look what you get when you plug in 0 for t. 0 wipes that out, you're at the point -6 for x and 3 for y, the beginning point I want to start with. If I go to t equals 1, I'm actually adding those components respectively to -6 and 3. So -6 plus 14 takes me to +8 for x. +3 minus 8 times 1 takes me to -5 for y. So that'll always be your span for t when you're parameterizing a line segment. And sometimes the problem will give it to you. It'll say, boom, here's your parameterization, 0 to 1 for t, and then now go and evaluate your line interval. But just to make sure everyone's on the same page, because I wasn't here when you were taught that, I just want to make sure it was something kind of consistent to this. But that might be something that was probably glanced over because it really doesn't play a big role until now. Usually you're just coming up with that and you don't have to define this. But here we do have to define this because these become your integral limits on the line interval. So you need to have those t values given. So since I parameterize this segment, beginning here and ending there, I can use 0 to 1 for my t values. Okay? So all that's my c stuff. Put a little box around that so I can refer back to it later. So that's one thing you need. To correctly evaluate one of these types of line intervals, you need to have your curve in parametric form. And again, just looking at the homework, sometimes it's given to you in parametric form. Like in this first one, I tell you x is t squared, y is 2t, 0 to 1 for t. So sometimes you don't have to do the parameterization yourself, but sometimes you do. Like in this second one, you're asked to parameterize the right half of a circle of radius 4. And then I guess oriented, one way clockwise or counterclockwise, whichever way you want it oriented. But sometimes you have to come up with that particular parameterization yourself. Here's a 3-dimensional line segment you have to parameterize. Works the same way. So you have an x equals y equals z equals triplet of equations. You got your beginning point, head to tail, or tail to head, do your vector to get the t coefficients, and it works the same way in 3D as it does in 2D. So sometimes you have to come up with the parameterization yourself, and sometimes you don't. So I wanted to show you kind of, I guess, the worst case scenario here is when you have to come up with it yourself. But now, how to actually do this line integral. What you want to do is you want to place x and y, replace the x and y in the integral with their parametric t expressions. So here's where we're actually doing the line integral part itself. Okay, so this is one of these ds types of line integrals. So f is given to you in the problem. And part of the evaluation of this, you're going to make replacements for the x and the y here, and that was given in the function. Well, according to that second line there, you want to replace the x and the y that you see here with their parametric counterparts. So I want to replace every use of x here with 1 minus t, and every use of y with t, because that's the y part of the parametric equation. But then you got to come up with this. You've never integrated with respect to s before, but do you remember what s stood for in the past? Arc length. Yeah, you're technically integrating with respect to the arc length of the underlying curve. In this case, that line segment that's in the xy plane that connects those 2 points. So your arc length here is not going to be too hard to deal with. But there is something to replace the ds with. So looking at that third instruction, after you replace x and y with their parametric equations, and let me do that, replace x with 1 minus t, and then replace y with t. So that's technically my x squared plus my y squared. I've just made the literal replacements with x and y in terms of their parametric definitions over here. So that's why you need the parametric curve, so you can see what to replace x and y with. The ds gets replaced with this arc length compensator. Earlier this semester, I think, you may have done arc length, in terms of the square root of x prime squared plus y prime squared for parametric curves. Maybe. It's been a while since you've seen that. But that's essentially like a differential compensator to turn your ds into something in terms of dt. So ds equals big square root of, again, originally it's x prime squared plus y prime squared. I'll write the shorthand right there. But then I actually want to make the replacements. X prime, where do you think that's going to come from?
Your x equation over there.
Yeah. Every use of x and y and z, if it's there, always refers back to the parametric equations, because this integral is going to be an integral in terms of t by the time we're done setting it up. I've replaced x and y with their parametric equation counterparts right there. The reference of x and y here means take the derivatives of your parametric equation. So the x prime squared part is technically negative 1 squared because you're doing the derivative of 1 minus t. So x prime, its derivative with respect to t would give me negative 1. It gets squared because of the way the arc length works. And then plus y prime, go back to y's definition, its derivative with respect to t is 1. So you place that with 1 squared. And you've now transformed this into an integral that I guess you can evaluate. It's in terms of one variable. The only thing missing are the limits. And the limits, like everything else, always go back to the parametric equations. Anything you need to replace in terms of x's and y's or x primes and y primes come right there from that family of stuff. Okay? And then the actual limits. The integral limits themselves are the t values that define your parametric curve. So the integral is, usually defined as being from a to b. Since this curve exists for t equals 0 to 1, they become your integral limits. That's how you create a line integral of this ds type. And so it always turns into a Calc2 single variable integral. You only see one use of double integrals in this set of material. It comes up later with surface integrals. But right now, everything's a single integral, just a good old Calc2 integral, after you know how to transform it. Let me double check with you all with the construction process, just to make sure everything's okay. So once it's built, now you're just going to want to evaluate it. Integrating from 0 to 1, that's going to be 1 minus 2t plus t squared plus t squared. So if you don't mind, that's what all the t stuff whittles out to whenever you FOIL and collect your like terms. What's this going to become? Your square root expression.
Root 2.
Root 2. Yeah, and since it's a constant, and notice there's a little times right there, and I've kept this group kind of factored out from it, because it technically is, in most cases, something you can factor out to the front of the integral. So you could pull that root 2 to the very front, like this. And then you're focusing all your integration attention on the t variables that come from the x squared plus the y squared. Okay. So let me draw a little line there to show you where that square root of 2 comes from. Pull that to the very front right there. And then, back in Calc 2, square root of 2 is pulled out. My antiderivative is t minus t squared plus 2/3 t to the third. The handy thing about line segments is you're always going to have 0 to 1 for your t values. And 0 to 1 are like the sweetest limits when you're integrating polynomials. You just plug in the t equals 1, and it gives you those coefficients, 1 minus 1 plus 2/3, and then 0 when plugged in wipes everything out. So what you end up with is this value. 2 root 2 over 3 is the value for this particular line interval. And again, what it measures, it's using this curve C as your x-axis of integration for like a Calc 2 integral. So instead of integrating from left to right, you're kind of integrating diagonally down here in the xy plane along that curve. So if you turn it into an area problem, this is the domain of the integral. These xy coordinates are projected upward to this paraboloid to generate a two-dimensional, kind of like a sideways sheet with the paraboloid cutting into the top of it. So the area of this surface right here, along that little segment, that has an area of 2 square root of 2 over 3 square units. That's the area of this thing. Let me try to color code it in red.
And that's just like a plane.
Yeah, it's a plane. Based on the skewed view, you can't see behind it, but it's understood just to be that one line segment projected up through the paraboloid. You see? So, in other words, I could walk behind this, and the paraboloid would be to my right, and the plane here would be to my left. So there's a space behind this. It's not solid. It's just a two-dimensional sheet projected up to the paraboloid. So it's intended to measure that thing's area. Okay, so I guess a better picture that I could give you for what line integrals kind of measure is if you got a function defined out here in 3 dimensions, looks something like this. Okay, so it's some kind of sheet or some kind of surface out here in space, and down here's the xy plane underneath it. Okay. So there's some curve down here in the xy plane defined as C. And I'm misleading you by, everybody's misleading you by calling these line integrals. You're not always integrating over straight lines. This example was integrated over a straight line, so the use of the word line for line integral kind of makes sense. But really you should call these curve integrals, because the domain of the integral doesn't have to be a straight line. It could be any kind of loopy sort of curve down here in the xy plane that begins here at t equals a and stops here at t equals b. So a more thorough picture of what this line integral measures is if you've got a parametric definition for this curve down here in the xy plane. This is kind of like our line segment that went from 1, 0 to 0, 1. We're projecting its points up to the surface like this. And so since this surface has sort of an organic shape to it, whenever this curve comes up here and meets this surface, it makes some kind of, funky design or something, maybe looks like that. Okay. So what this measures, the line integral over the curve C, down here, for this function f of x, y, with respect to the arc length of the curve itself, is measuring the area of this sheet that has the curve C as its base, and the function is serving as the top of the sheet. Okay? So it's just kind of like a calculus 2 integral that measures area. The only difference is it has to be represented in 3 dimensions, you see. Because if you're integrating over a straight line, you could liken that, you could even liken this to a 2-dimensional situation. Because you're integrating over a straight line, that plane that juts upward to the paraboloid is really just a 2-dimensional sheet. and you're finding that 2 root 2 over 3 is the area of its surface. Well, in this case, if your curve is more defined like a ripple like this, you're still projecting it up to the surface f on top, and this calculates that thing's area. So it really measures a two-dimensional quantity, but you see why you need 3 dimensions to represent the picture of it. Because if your curve down here is not a straight line, if it's got some ripple and curvature to it, then it's going to have to do this whenever you project it up to the surface on top. So this is still an area. It measures the area of this thing right here, going from the curve in the xy plane up to the function itself. Okay? So let me show you one more, because I get the feeling of sort of collective doubting Thomases out there. Let's see. Let's do this one right here on B, where you're asked to evaluate the curve, the line interval for the function xy to the fourth, and the curve C is the right half of a circle of radius 4. Okay? So let me grab a piece of paper. And as you look through the homework, you're going to see that my labeling system, it kind of stinks, because I've got these set up as capital A is the first section, vector fields and line intervals. Then there's capital B for the second section, capital C, capital D, capital E. So there's 5 sections in this homework packet right here, all right, A to E. Within A, there's number 1, parts A through D, lowercase. There's number 2, parts A through B. Number 3, parts A, B, C, D, and so forth. So sorry about the uppercase, lowercase, alphabet soup that I'm throwing at you, but it's at least systematic, and it is relatively ordered. So if I actually pair this problem with its correct placing, it's homework section A, problem number 3, and then subproblem B of number 3. So I apologize if you feel like you're playing Battleship, but it's just the way I have these things labeled. So the curve for this line interval is the right half of the circle of radius 4. So if it's the right half, we're looking at something like this. Okay. And let's see, in terms of projecting it, or giving it an orientation, let's just stick with the same orientation you've always done in the past. Anytime you deal with circles, when you pair x with cosine and pair y with sine, you're using the same orientation you've always had on circles, counterclockwise. So always remember, if you're parameterizing part of a circle, the most convenient linking is going to be this. Pair cosine of t with x and pair sine of t with y. This would guarantee you a circle of what radius? 1. If you want to stretch it to a radius of 4, just stretch your sine and cosine amplitudes by 4. That'll guarantee you have that circle of radius 4. What t values are going to guarantee we get the right half of it? Because keep in mind, what are values of t here going to represent for this curve? Think in terms of polar coordinates. Okay, you want to end at pi over 2. You're right, because you're stopping. If you want to orient it this way, to where you stop it there, right there at the top, you're going to want to stop at pi over 2. So I'm going to say pi over 2 is our. Oops, wrong direction. Usually these inequalities are given as a less or equal to t less or equal to b. So you want pi over 2 to be your last value. If you want to stop up there on the y-axis at the positive 4. If you want to begin down here at the y-axis at negative 4, what do you want to start with?
3 pi.
Awesome.
Negative
If
pi.
you could start at 3 pi over 2 and then go to 5 pi over 2.
But you have to go to 5 pi over 2. It's the same rule as theta for polar intervals. You got to make sure your t values are increasing. So if you commit to pi over 2 as the last, you want to stick with negative pi over 2 as the beginning. Or, like Kai reminded us, you could also say 3 pi over 2 to 5 pi over 2 as long as it is an increasing range of t. Okay? So it's kind of like, just like polar coordinates. It is. You're using an r value of 4, so r is fixed. But t is like the variable theta, because you want to go from the bottom half to the top half of the circle. So I've got my curve. The way this sets up is every x gets replaced with its x equation here, every y with its y equation there. So I know my interval is going to have to go from negative pi over 2 to pi over 2. I'm actually beginning the construction process of the line interval itself. Okay. X, y to the 4th, x gets replaced with 4 cosine t. y gets replaced with 4 sine of t. And yes, preserve all the things that are done to x and y. X is to the first power, y is to the 4th power, so keep that 4th power there and they're multiplied together. And now I need to come up with the ds. Remember, ds comes from taking the derivative of your x and your y equations, squaring them, and adding them, like an arc length calculation. So open up a big radical, although this radical is going to kind of come into something pretty handy here if you do it correctly. X prime is going to be this thing's derivative, which would technically be negative 4 sine t squared plus y prime squared. Y's first derivative is 4 cosine t squared. And all this guarantees the differential of dt. Once you've made all these replacements for x, y, and the ds differential, you're turning it into a dt, or a t variable integral. So the radical in this one turns out to be something pretty nice. It should be 4. Yeah, by the time you square everything out, you've got 16 sine squared plus 16 cosine squared. If you factor out that 16, what's your sine squared plus cosine squared going to give you? 1. So really you're taking the square root of 16 times 1, which gives you a 4. So sometimes, in most cases, your square root expression doesn't turn into anything too terribly funky, especially if sines and cosines are involved. When you do the derivatives and square them and add them, you're always going to get that sine squared plus cosine squared love showing up. And so it turns into the square root of 16 times 1, so you get a 4. Now notice all these other 4s are in the mix. Be careful. I can pull this 4 to the front. So there's the 4 that came from my square root. There's another 4 right here for my cosine factor. But then there's a 4 to the 4th, which is 16, 256, right? So you get a pretty big coefficient in the front there. 2048? Okay, so I'll say that for the next step. That's just a coefficient. That is not,
4,096.
as I was told on somebody's test, that's not too, crazy a number. All right? But then what you're left integrating is a cosine t and a 4th power of sine t. So you got to stretch your brain to remember how to integrate something like this. If any of you have Fourier series in your future, you're going to definitely need to know how to integrate these things with sine and cosine.
I'm sorry, what is this?
Fourier series. Anybody taking partial differential equations at some point, possibly?
Most likely.
Yeah. If you're going high enough in engineering, you'll take PDEs at some point. So you'll be dealing with Fourier series and Fourier transforms, which boils down in some cases to sine and cosine product intervals like this. Okay. So do you remember how to integrate this thing?
That's make your U sign.
It's a U sub. That's all there is to it. Because the guiding principle for a U sub is whatever you choose U to equal, its derivative has to be a multiple I can pair with the dx or the dt or whatever. And you're committing to let a U equal sine t. What's the derivative of sine t? Cosine t. And I do have a cosine t factor in here that I can pair with the dt based on what du is supposed to replace. So this works really smoothly with a U sub. If you let U equal sine t, I've got this heinous 2048, was it? Coefficient in the front. This becomes
4096.
oh.
If you have 4 times 4 times 256 is 4,096.
4 because
Yeah,
the
4096.
It's 4096.
Yeah.
Oh, because I'm just doubling it. So let me put another times 2 there, so it's not technically wrong. So yeah, it'll be 4096 in my next step. So all this becomes du, and that becomes u to the 4th. And yes, I'm sorry, but Nicholas, I'm changing my limits. The lower limit is going to be sine of negative pi over 2 is -1, sine of pi over 2 is +1. Still, undo your u, plug in your negative pi over 2 and your pi over 2, it'll work out the same way. So 4096 times u to the 5th over 5, -1 to 1 limits. Oh, here's another one that you could double. That little doubling trick I mentioned on some of the answers to the test problems. That's an even function over a symmetric interval, so you could do times 2 again, and then 0 to 1. But anyway, neither here nor there. 4096 over 5 times 2 So eventually you do have to evaluate it because that's 1 minus negative 1. And 4096 times 2 is what, 90?
8192.
8192, because you do have an extra 100 in there. And none of it's divisible by 5. So that turns out to be the value of that particular line interval. And this one, I guess I could give you a picture with this. This is some kind of, surface up above that curve. So this surface would be entirely positive. So if this curve's points were projected upward to that surface, that object would have a square footage surface area. It'd be sort of like a half circle shape of that many square units. And that's kind of funky because you'd figure pi would be in the mix with something that's sort of rounded like that, but there's no pi there at all. You took away the trig, took away the pi's, it just turned out to be a rational number. Okay. If the picturing is troubling you, one thing you could do is just not try to picture it. I mean, if you want to the best picture I honestly can give you of what these things are measuring is something like that. Or the kind of generic picture that I gave you with this other example that I did right here. That's a rough idea of what these line integrals are actually measuring. Oh, you sure? So I'll include this example that's worked out with your notes. And then venturing forth, I want to go ahead and show you the f.dr type of line integrals. Okay? So these tie in a little bit with physics. And they're very similar to the DS type. The only thing missing is the need for the square root expression. That's not needed here. You're actually constructing your integral based on a dot product. And remember, a dot product produces what kind of quantity? A scalar. So when you set up a line integral for a dot product like this, you are eventually going to be integrating some scalar function. So just like in these DS types, going through this whole construction transformation process, you're ultimately getting it down to a calculus 2 integral in terms of the variable t. Every single one of these line integrals, the ds type, the f.dr dot product type, the dx dy dz type, all these turn into t intervals by the time everything is completely set up and properly substituted. So on this type, what you're actually, if you want to tie it in with a physics calculation, if you think of the vector f, that's going to be from a vector field. So these particular types of line integrals actually refer to a vector field in the problem. You have to be given some kind of vector field in reference to the problem. So the f in the integral represents some vector from that field, or a set of vectors that are used from that field. Okay? R is actually the path you're taking. So instead of it given in x equals y equals or z equals parametric form, it's given to you as a vector function, which still represents the same thing. See, this is the same thing as x equals 1 plus t squared is a parametric equation. Same thing as y equals t is a parametric equation for t going from 0 to 1. So sometimes your curve is defined parametrically. For the f.dr types, the curve is defined in terms of a vector function, but still, those are synonymous with parametric equations. Just make sure you pair x and y and z alphabetically with the I, j, k components of the curve itself. Okay? So you're calculating work done by a vector field and moving a particle along this curve. So the curve is given as a vector function, like I mentioned. The vector field's a function of x and y, also given in the problem. So the construction process. This is the actual kind of generic format for a f.dr type of line integral. What you have to do is, beginning with this next step, the vector field is actually initially a function of x and y, like this. So here's really your first step in the building process. In the vector field, boom, in this guy right here, is consistent with what we did with the ds type. You're going to replace x and y with their parametric counterparts. Because you're only focusing on vectors in this field, not at just any point in the plane. You only want to use vectors that are coming from that path. So that's why you're taking every use of x right here and replacing all the x's with 1 plus t squared. And you want to replace all the y's with t, based on this being their parametric equations. So that's specifying the only vectors in the field that are going to be tailed at points on that curve. Okay? So that's one way of I guess, specifying your vector field itself. So the vector field is originally xyi plus y squared j, replacing x equals 1 plus t squared and y equals t. The vector field becomes x times y, so did I do too much there? X times y, just multiply those two together, you get t plus t cubed for your I component. And then y squared for your j is going to be t squared. Just, making those literal substitutions for x and for y. So now my vector field is in terms of t. Okay? So that's the first step. Make your xy replacements into the vector field. Second, you actually have to calculate the dot product that's alluded to in this type of line interval. You take your newly formed vector field that's now a function of the variable t, because you've eliminated the presence of x and y, and you want to take its dot product with dr. Dr essentially represents what?
R dot R prime.
Well, not r dot r prime, or just dotted with r prime. You're really just wanting to do the dot product with the derivative of your path. So f dot dr is the same thing as f dotted with r prime. Okay, so copy down your f, and I'm gonna stop using the ij notation. I was just, I guess, doing that for emphasis. The vector field f here has t plus t cubed as its I component, and has t squared as its j component. And I'm going to dot it with r prime. So keep in mind, you got to do component-wise derivatives here. This is r that's given to you as the path of the particle through the field. So its I component here would be 2t, and the j component will be 1, because you're really doing x prime and y prime right there. So the derivative of your parametric equations come up in the mix as well, but not like the square root expression from the ds type that comes up in this dot product calculation for f dot r prime. And then make your scalar. That's going to turn into, multiply the I components together, that'll be 2t squared plus 2t to the fourth, and then plus 1t squared. And so that turns out to be your integrand. I think I did my dot product correctly. 2t squared plus 2t to the fourth plus 1t squared. So this is your actual integrand itself. And it's all in terms of t now. That's what you actually put inside the integral that you're going to be, calculating the work from. So then, step 3, we've already built everything in step 3. The actual integral is calculated this way. This is sort of the abstract version of the line integral, but here's the nuts and bolts of what we did. We took the vector field f, we plugged in the r equations for x and y in for x and y in f, and did its dot product with r prime. And so this is what we ultimately want to integrate. So again, I don't mean to call this the useless form of the line integral, but this is sort of the theoretical form of what your line integral starts as. The nuts and bolts, what do I actually evaluate for, is this guy right here. After you've done all this substitution and dot product construction process. And your integral limits is consistent with the same as the ds type. It's the t values that define your parametric curve. So this curve was defined from 0 to 1 for t. So once again, that becomes your a to b limits, 0 to 1 in this case. Now, since this is calculating work, can this interval, a work interval be negative?